Today we're going to talk about forces and the laws of motion. So it's Newton's second and third laws. Newton's second law. Force is proportional to mass and acceleration. Okay? The more massive objects require more force to accelerate. Okay? Back to the example. The dump truck versus the little car. It takes more force to move a dump truck than it does the car because of the difference in mass. So Newton's second law is the acceleration of an object is directly proportional to the net external forces acting on the object and inversely proportional to the object's mass. I know, you're going, huh? Let me put it a little easier to understand. Here's your formula. This is Newton's second law. Force equals mass times acceleration. Don't panic about this little backwards E here. All that means is the sum of net external force, the sum of the forces, equals mass times acceleration. That is Newton's second law. F is the vector sum of all the forces acting on an object. Okay, it's all the forces. M is mass, A is acceleration. We just talked about acceleration in the last chapter. And at some point, we will be breaking down the force and acceleration into x and y and using Pythagorean's theorem to find net force and direction. Don't panic on that part because I will show you how to do it when we come to it. So, Newton's second law. Newton's third law. Forces, to include the field forces. Remember, there's two kinds of forces. There's contact forces, and then there's like the magnets, or like gravity, or field forces. There's no contact. Always exist in pairs. When you apply a force to an object, the object returns that force to you. So, Newton's third law. If two objects interact, the magnitude of the force exerted on object 1 by object 2 is equal to the magnitude of the force exerted on object 2 by object 1. And those two forces are opposite in direction. Easy way to remember it, opposite but equal. So what does that mean? That's a mouthful. So for every action force, there is an equal but opposite reaction force. There's an action-reaction pair of a pair of simultaneous equal but opposite forces. Okay. Action and reaction forces act on different objects but involve the same two objects. Huh? Okay. In your mind's eye, you're leaning against a wall. Okay. You're putting force on the wall, and the wall is pushing back equal but opposite. If my force was greater than the wall, I would go through the wall. If the wall's force was pushing greater than I'm leaning, I would topple over. Okay? Opposite but equal. I'm leaning on the wall is pushing back, opposite but equal. It's an action-reaction pair. So opposite but equal. Here's an example. I am nailing a nail into a piece of wood. Look at the nail. The hammer hits against the head of the nail. So that force is going to the left. Where the nail is touching the wood is pushing back on the nail. So opposite but equal. At some point, the hammer, if you hit it hard enough, is going to have more force than the wood pushing back, and so the nail will go into the wood. But in this case, as it's pictured, the nail's not moving, the hammer is not bouncing back the other way. It's opposite but equal. And that's it. Starting on Monday, we're going to do a worksheet. It's a conceptual worksheet. You don't have to worry about the equations, but to see if you can identify how Newton's first, second, and third laws are applied. Okay? So, get your notes written, get them in your notebook, come show them to me, or submit them on Schoology. Thanks.